Assalamu alaikum. Good evening. Welcome, everyone. I am Ahmed Al-Mihiri, Assistant Professor of Physics in the Division of Science here at NYU Abu Dhabi. It is with great pleasure that I welcome all of you here today for this ambitiously titled event, where we're going to get a glimpse into the most recent advances in our understanding of the structure of the universe, and importantly, into the intellectual effort it takes to make them. I'm eternally grateful to the Division of Science at NYU AD, to the UAE Space Agency, and to the NYU AD Institute for supporting and organizing this event, as well as the scientific conference that's been taking place this week. If there's anything everyone in this room agrees on, it is the importance of science, and that it plays, the importance of science and the importance of the role that it plays in shaping how we understand our place in the universe, as well as in transforming our lives for the better. Nobody here personifies this principle more than Her Excellency Sara Amiri, Minister of State for Public Education and Advanced Technology, who's made it her mission to support science in the UAE through shaping the UAE's science policy. Join me in welcoming Her Excellency to the stage to make a few remarks. Please.
Assalamu alaikum. A very good evening to everyone. It gives me great pleasure to be here with you at NYU Abu Dhabi's campus and at this great discussion that you've had throughout this week and also on this session. I'd like to extend a warm welcome to all of you at New York University Abu Dhabi as we gather here at the Abu Dhabi meeting on theoretical physics. Today we come together as a community of leading scientists, researchers, and academics to share knowledge, expertise in pursuit of a common goal. Science and technology remains a pillar of development for the Emirates. It remains a mechanism for transformation, a tool for growth, and a tool to enrich the community overall and ensure that our institutions become drivers of change. Theoretical physics and the role that NYU Abu Dhabi plays in this overall ecosystem is vital drive for the change and transformation that we want to see in the country moving forward. As we continue to prioritize and shape our science and technology ecosystem, space is a vital driver. Our natural sciences are the transformers of this overall change. Our priorities through the Emirates Research and Development Council continue to be shaped around driving immediate change and utilizing research and development as one of the tools to transform challenges into opportunities. But we are also driving towards ensuring that fundamental science and research at universities continue to be the driver for knowledge creation, the driver for talent, and the mechanism by which we continue to become a hub for talent for the region and with impact across the world. I love the context and the mechanism by which this entire congregation has come to be, the priorities that it brings to the table, the role that theoretical physics can play in NYU Abu Dhabi. And I'd like to thank Professor Ahmed Al-Mihiri for the big drive. I think I recall us having this conversation many years ago in New York on creating this vital hub, and we are here to support you and support the team at NYU Abu Dhabi and support also your wider ecosystem to ensure that theoretical physics has a place not only in the Emirates but also has a place in the region. Thank you.
Okay, next up, I wanted to introduce today's lineup. The event this evening will be composed of 3 20-minute talks, followed by a panel discussion that I will moderate, after which it will be opened up for questions from the audience. So please take notes. Next, all right, so let me introduce the speakers. Our first speaker is Juan Maldacena, the Carl P. Feinberg Professor at the Institute for Advanced Study. Juan got his undergraduate degree from Balseiro Institute in Argentina. He then got his PhD from Princeton University and went on to be a professor at Harvard University before settling down at the Institute for Advanced Study. Juan is a trailblazer, or I guess you might call him in today's lingo an influencer in the field of theoretical physics. And his paper on the holographic nature of gravity continues to be the most well-cited paper in the field. The second speaker is Kumrun Vafa, the Hollis Professor of Mathematics and Natural Philosophy at Harvard University. Kumrun got his bachelor's from MIT and then his PhD from Princeton University under the supervision of the famed Edward Witten. I'm sure many of you know Edward. And then went on as a professor at Harvard University, where he's been ever since. Kumrun has made foundational contributions in our understanding of black holes through the lens of string theory, counting precisely how many different ways is there to be a black hole. And last but not least is Nima Arkani Hamed, professor at the Institute for Advanced Study. Nima got his bachelor's from my alma mater, the University of Toronto, and his PhD from the University of California at Berkeley, and went on to be a professor at Berkeley, at Harvard, before finally settling down at the Institute for Advanced Study. Nima is famed for his mastery and contributions into particle physics, proposing new physics models that could potentially lead to experimental signatures. Now, it would take the entire night to list all of the awards that all of these speakers have gotten over the years. I'll just mention one. They each got the famous Breakthrough Prize from the Breakthrough Foundation, and that way you know that they're all millionaires. And with that, let me give the stage to Juan.
Okay, thank you, Hamed. It's a pleasure to be here, my first time in Abu Dhabi. I've been enjoying the conference. I've been enjoying getting to know the city, and I hope you enjoyed the talk. So I'll be talking about black holes and quantum information, and first I'll give you a quick summary of what I will talk about. So we'll first talk about black holes, how general relativity gives us black holes. Black holes are very confusing. Einstein was confused about black holes. He thought that they didn't exist. So if you are confused about black holes, don't worry. You are in good company. But then they were understood better. And it was understood that stars could collapse into black holes and that there could be black holes in the sky. Then they are so confusing that even the name was chosen wrongly, because Hawking discovered that black holes can sometimes be white. I'll try to explain why that happens. And not only that, but he thought that black holes will lead to a contradiction with the laws of quantum mechanics. And, I'll then talk about some more recent developments that resolve some of these contradictions that Hawking had proposed using new ideas by some of the people here present. Okay, so let's start talking about gravity. You all know the most intuitive fact about gravity, that if you drop something very heavy, it falls more quickly than something light. That's what Aristotle said. But then Galileo realized that if you remove the air, both things, heavy or light, they fall exactly in the same way. So you have to remove the effect of the air resistance. So in the vacuum, they fall exactly in the same way. And this led to what Einstein called his happiest thought. It was the idea that when you fall freely, gravity disappears. So it has this funny feature. So for example, if you are an astronaut orbiting the Earth together with your spacecraft, it looks like you are floating relative to your spacecraft. Both are being moved by gravity, and both are subject to the force of gravity, but you are floating because you are essentially falling freely. And Einstein took this idea and a few others and developed the idea of the theory of general relativity, which is our modern theory of gravity. So let me quickly explain what that theory is about. So the basic idea is that gravity is due to the geometry of space-time. So the first confusion is why you put time and space together. Well, the laws of motion and the special relativity, so the relativity of moving observers, tells us that time and space are mixed together, and we'll see that when we talk about the geometry of space-time, it's important that time is deformed in a certain way. So a heavy object curves the space-time around it, and the idea is that when you have a particle moving in that space-time, that particle chooses the, in some sense, shortest path, or more precisely, the path of longest proper lifetime. Now, Einstein's theory made very surprising predictions, and there were, one was the expansion of the universe, and the other one were black holes. They were so surprising that Einstein himself was surprised about them. So for example, Einstein doubted these two predictions. In fact, he told one of the creators of the idea of expansion defined in universe, your mathematics is excellent, but your physics is dismal. And I love this phrase because we use a lot of mathematics, and that's what people tell us sometimes. Now we will discuss black holes. We'll focus on that aspect. But before we discuss black holes, let's talk again about gravity and what it means for space-time to be deformed, right? So what it means in particular is that if you have two clocks on a building, the clock on the top will run faster than the clock in the bottom, okay? So if you want to remain younger, you live in the bottom floor. Of course, this is a very small effect. It's 1 part in 10 to the 15, very, very small. My watch doesn't tell that difference. But we have atomic clocks that can tell a difference in height of a few millimeters. So that's the world record. So that's what it means in practice for space-time to be deformed. Now, soon after Einstein had his equations, Schwarzschild solved these equations and found the geometry outside the massive body. So if you have a star that has some mass, he found this geometry outside, and the geometry outside tells us, among other things, how time flows at a certain position. So if you are far away, time flows with some certain rate. If you are closer to the surface of the star, it runs a little more slowly. Remember what we had said about the building, right? And then the observer that is sitting here will feel some weight. Now, if you take that same star and you make it smaller, keeping the mass the same, then what we see, this fortunately wasn't supposed to happen. Okay, well, sorry, I was pressing the wrong key. That key. Okay, so why is it not running? Sorry for this mishap. So if we make it a little smaller, then the clock will run a little more slowly than here and also than here, and the person will feel a larger weight. But the surprise was that if you make it smaller than a certain radius, which we now call the black hole radius, something very weird happened. It looks like time completely stops, and the person would feel an infinite weight if he's standing at that position. And this is what Einstein thought was ridiculous. This couldn't possibly happen. And I would have thought the same thing also. So this is very surprising, and it took some time to understand what's going on. And one important property about these observers is that they are not falling freely. So the question is, remember, one of the principles is that gravity disappears when you're falling freely. Is it true also when you are falling freely in this region of the space-time? And yeah, it is true. And in fact, if they fell freely, you find that the geometry actually continues behind that surface. And nothing special happens when you cross that surface. But after you cross it, you encounter a region of space-time that is collapsing. It's a bit like a Big Bang in reverse. So it's a collapse of the universe where the curvatures are getting very high, and the tidal gravitational forces are stretching us in some directions and compressing us in other directions. So it would be very unpleasant, and we would die. Okay? So it's not good to go into a black hole. But we will not feel anything special when we cross the horizon. And there is that singularity, that point of infinite curvature, but that is at the end of time. So the interior is really into the future of this horizon. It's not somehow something that the singularity is inside, some point inside, is some point in the future, some region in the future. Now, what does the word singularity mean? It just means we don't know what's going on. So if you don't know what the word means, we also don't know what it means. The theory breaks down, and we expect that quantum mechanics should play a role there. Because at the singularity, so some regions of space become very, very tiny, and quantum mechanics is important for small things like atoms and things like that. And for that reason, we think that space-time now has to behave according to quantum mechanical laws. Now, on the other hand, if we stay outside, we don't see the singularity, and from the outside, we are perfectly fine. Okay, we can calculate exactly what happens when you are outside. So for now, we will talk about black holes as seen from the outside. And now some lessons that have been learned about black holes is first that once you cross the horizon, then you cannot come out, and that's why it's called the horizon. And that stars can collapse into black holes if they are very massive enough, and that there are objects in the sky that actually seem to be black holes. So let me briefly mention real black holes. They can be produced by the collapse of massive stars, or they can be at the center of galaxies. And how do we see them? Well, we see them through various ways. So one very nice way to see them is when two black holes collide, they emit gravity waves that we can detect here on Earth, and we can compare the predictions of the gravity waves obtained through Einstein's equations to what is observed, and they seem to agree very well. So this is a new technique since 2016 when the first observation was made. Then there are black holes at the center of galaxies, and so you can have, for example, one galaxy, the M87 galaxy, that has some weird features of jets of particles coming out, and people had theorized that perhaps there is a black hole in the center that produces these jets. People got closer looks, and there seemed to be something weird at the center, and most recently in 2019 we got a nice picture of this region near the center that has a size comparable to the size of the black hole, which is roughly that size in the middle, and the light is produced by some gas that is around the black hole and is being lensed in the way that you expect as if a black hole was present there. And not only M87 has this picture, but also more recently we had a similar picture from the center of our own galaxy. So we're really in a golden era for black hole observations. So black holes started in 1916 when Schwarzschild found them as very confusing theoretical mathematical constructions, and now we are seeing them with our telescopes. Okay, so the next of the talk will be about some more theoretical aspects of black holes, so that haven't been observed yet. So first we'll discuss some interesting theoretical properties of black holes, just according to the Einstein theory. So black holes are very special, and the first property I want to discuss is the fact that they are very universal. So the final shape of a black hole is independent of how you form it. So we can have stars that have different colors, different chemical compositions, different shapes. But on the other hand, if they were to collapse to a black hole, they would be only characterized by their mass. They might have some angular momentum, so they can be rotating, and they might have a bit of charge. Typically, the ones that are really produced by stars, they don't have any charge. So they're characterized basically by two numbers, the mass and the rotation velocity. So that makes them very special. So as a comment, I just mentioned that the ancients thought that all the heavenly bodies were perfect spheres, right? The moon was a perfect sphere, the sun was a perfect sphere. Now we know that they are not perfect spheres, but the classical theory of general relativity predicts that a black hole, a non-rotating black hole, is a perfect sphere. Okay? So we still have some perfect spheres in our cosmology. Now, the second point I wanted to discuss is some interesting property of these black hole collisions. So the result of the collision of two black holes is something fairly complicated, but you have to calculate it with computers. It's difficult with very sophisticated programs that only recently were made to work and so on. However, these equations have a very simple property, which is that if the two initial black holes have certain areas, then the area of the final black hole should be bigger than the area of the two initial black holes. So it's a curious property of the equations that something simple. You don't need to do any calculations. There is a simple argument that Hawking found to argue for this. Now, total mass of the black hole could decrease, but the areas should always increase. Now, so far we discussed black holes according to Einstein's theory of general relativity, which is a classical theory. But when we include quantum mechanics, there is a new surprise. And this is the surprise of the white black holes that we were talking about. Now, what is that? So Hawking solved the equations for a quantum, used the laws of quantum mechanics to predict how quantum particles would behave in the vicinity of black holes. And through some arguments whose details I'm not going to discuss, he found that the black hole would start emitting particles that will look like particles emitted by a hot body. So in the same way that a hot, let's say, piece of charcoal or emits radiation, the black hole would also emit radiation at some characteristic temperature. And the temperature of the black hole increases when the black hole size decreases. So a black hole that is very big will have very small temperature, and as you make it smaller, it will have higher temperature, it will look red, and then you make it a little smaller, it will look white. And if you make it small enough, the temperature could be similar to the temperature at the surface of the sun, and then it will look white to our eyes. If you make it even smaller, it would be even higher temperatures. So for black holes that are of astrophysical sizes, so the sizes that are naturally produced in the universe, this temperature is very, very tiny and cannot be measured. Well, it has not been measured, and it's hard to imagine how it could be measured. On the other hand, you would need a black hole of roughly the mass of a continent that would have a size of a bacterium for us to see it white. Now, so this is, so let me just mention the experimental evidence for this effect. Now, there is now experimental evidence for this effect for the case of black holes. As I said, it's very small. It's a very tiny effect, so it's a theoretically predicted effect. We are very confident that our theories predict this effect. On the other hand, there is a very similar effect that occurs in an expanding universe. So in an expanding universe, there is a sense in which there is also a horizon, and there is also a sense in which there is a temperature. And the same equations that you can use for black holes, you can use for the expanding universe and find this temperature. And for the particular case of the expansion of the universe, in the far past, the universe was expanding very rapidly, and that temperature was an important effect. And in fact, that temperature is our best explanation for the origin of the anisotropy that we see in the cosmic microwave background. So if we look around the sky, we see some microwaves coming to us, and they have we have different amounts of microwaves at different points, and we think that that's an indirect confirmation, if we wish, of this effect, and it's something that we use to describe the universe around us. So some lesson that we learned from black holes had also some consequence in the case of cosmology. Okay, so if we imagine that you form a black hole, it will, as it loses mass, will have a final lifetime because it emits this radiation. But for a black hole that is very massive, like the mass of the sun, for example, this lifetime is longer than the age of the universe. However, if you had a black hole, if you were able to make a black hole with a mass of, let's say, 100 kilograms, it would make a huge explosion. It would be very, very fast. You wouldn't want to be near that. Of course, it's very difficult to do that, so don't worry, no one will do it. Now, one reason that this effect is surprising, this Hawking radiation effect, is that in physics we think that temperature is due to the motion of the microscopic constituents of matter. So for example, if we have hot air versus cold air, the only difference is that for cold air, the molecules are more slowly than for hot air. And so there is some microscopic constituents that is moving. And in the case of the black hole, we don't know exactly what these constituents are, or at least in principle, the general relativity does not tell us, obviously, what these constituents are. However, the laws of thermodynamics give us some relationship between the temperature and the energy and the amount of quantum information that we need to specify the positions of all these constituents. It tells us in how many ways we can arrange the constituents or the molecules of the air in the previous transparency. And those we can just figure out directly from the laws of thermodynamics. I won't give you the details, but this is part of completely established physics. And if you do it for a case of a black hole, you find that that quantity, that quantum information or entropy, is given by the area of the black hole in units of some length scale, which works out, which is a combination of the Newton constant, h bar, and the speed of light, which works out to be 10 to the minus 33 centimeters. This is a very, very, very super tiny distance. It's a distance much, much smaller than the smallest distances we can see today. But it's a distance that just comes from the fundamental constants. And so if you have a macroscopic black hole, you will have a huge entropy. So. Now, something interesting about this formula is that that area law that Hawking had found as a curiosity actually translates into the second law of thermodynamics, which says that this entropy should always be increasing. So entropy is somehow also a measure of disorder, and is one of perhaps the most intuitive laws of physics, that disorders always increases. That's the second law of thermodynamics. Now, these results have inspired a certain hypothesis, which is the idea that black holes can be viewed as quantum systems. So the idea is that if you have a black hole and you look at it from the outside, we could replace that black hole by a set of quantum bits, qubits, so the basic unit of quantum mechanics, that are interacting in some way and evolving according to the laws, standard laws of quantum mechanics. We don't know exactly how they are interacting. We know that there should be a system that describes this. And in some model situations, in the theories we work on, like string theory and so on, that you'll hear in later talks, we can give precisely what this system is. So we have some examples where we understand exactly what that system is. However, not everyone agreed with this idea. And in fact, Stephen Hawking famously argued that this cannot possibly be true. So it cannot be true that that picture cannot be true. And this is the so-called information loss problem. And it's a problem only if you believe in that picture that we said before. And so he basically said that we can form a black hole with essentially cold and ordered matter. So very cold stuff. You form the black hole with a very low, let's say, entropy state, or very low information, containing very low information. And then, on the other hand, when the black hole emits radiation, this radiation is hot and is disordered in some way. So we went from an ordered state to a very disordered state. And the quantum mechanics would not allow for that. So in some sense, so if you were able to completely calculate what comes out of this process, it should be at least secretly ordered. So quantum mechanics says that there should be some subtle information in the outgoing radiation, and that makes it ordered, and the disorder is just only apparent. But if you were able to calculate exactly what's going on, you would be able to see that it came from an initial ordered state. On the other hand, the general relativity tells us that that matter that formed the black hole is deep into the interior, in a region that cannot send any signals to the outside. And for that reason, he argued that you will lose this information. Now the question is who is right? So. But before trying to answer this question, let me try to explain a little bit the philosophy behind this line of research. So why do we care about this question? So we care because we think that understanding quantum aspects of black holes will help us understand some aspects of cosmology. And this is something that, as I reviewed, already happened. So we think that by understanding more aspects of black holes, we'll understand more aspects of cosmology. In particular, there is some aspect of cosmology we don't understand, which is the initial singularity, what happened in the very first instance of the Big Bang. And that instance is very similar to the black hole singularity. So black hole singularity is sort of the time reverse of that, the big crunch. And And the black hole singularity involves quantum mechanics. So it involves putting gravity and quantum mechanics together. And this black hole information problem also involves putting gravity and quantum mechanics together. So we are at least going in the right direction. So in some sense, the black hole case, we focus on black hole case because it's simpler. It's a situation where singularity is only in the interior. We can remain outside the black hole and analyze the system in a simpler way with tools that we already know. So who's right? So is either Hawking saying that quantum information is lost into black holes, or perhaps many of us who think that it's not. Now, there's been recent progress in this problem, and it is due to basically new formulas that compute the amount of quantum information associated to a black hole. We already saw an old formula, which was the formula that computed the area of the horizon, which is the so-called thermodynamic entropy, which can be viewed as the maximal amount of disorder that the black hole can have. But sometimes the black hole, if it was formed in a simple way, might have a slightly less, it might be slightly less disordered. So there's another formula that allows us to compute more precisely how disordered the black hole is, or how much quantum information could be contained by that black hole configuration. And so it is also an area formula. It's a formula that computes the area of some surface. So it's a geometrical formula, somewhat similar to the one giving us the area of the horizon. I won't give you the details of exactly how to find this formula, but I should just only say that given the space-time geometry, so if you have a solution of Einstein's equations that you got somewhere, you go and look for a certain surface that has certain properties, another mathematical problem you can solve, and that would give you the amount of quantum information that can be stored in, let's say, this geometry. And this formula also depends on features of the black hole interior. And so this formula was developed, as I mentioned here, from 2006 to 2014. And in 2019, two groups of people, Ahmed and collaborators and Jeff Pennington, used this formula to essentially compute the entropy coming out of Hawking radiation. And they found that in order to really compute the quantum information in that Hawking radiation, you also had to look for a certain surface with certain properties and that depend on the black hole interior. And when they went and they computed the area of this surface, they found that the entropy agreed with what you expected to see from the quantum mechanics point of view. Let me try to explain what that, how am I doing with time? I'm doing badly. Okay, let me just say that there are two curves, and they found that the right curve is right. So in conclusions, black holes are fascinating objects where the deformation of space-time geometry is very drastic, and they have many interesting aspects. We understood an important aspect of quantum gravity recently, and there are many mysteries. But we are living in a wonderful era for the study of theoretical aspects of black holes, and there are many questions that we still don't understand, in particular the black hole singularity and the beginning of the universe. Thank you very much.
مساء الخير. أنا سعيد جدا بمشاركتي في هذا اللقاء الذي تنظمه جامعة نيويورك في أبو ظبي مع وكالة الإمارات للفضاء، وأتمنى أن تساهم هذه الخطوة في تعزيز النشاط العلمي في هذه الدولة الجميلة التي تنمو بسرعة هائلة. I'll spare the rest of my bad Arabic accent and continue in English. So it's a pleasure to be here in this beautiful country and talk about science. In this rapidly growing country, hopefully science will be in the same direction as the rest of the country is growing. I'm going to talk about some aspects of string theory and the observed universe. Fundamental forces and matter, without gravity included, are well understood. They are beautifully described by quantum interactions of all elementary particles with what we call Feynman diagrams. However, when one tries to add gravity into the mix in the form of gravitons, the formalism breaks down. And the computation of physical processes leads to incurable infinities, similar to infinities or singularities that Juan was mentioning. And this naively suggests that gravity is in conflict with quantum theory. They don't seem to exist together. But of course, it cannot be true, because we live in a universe where we do have gravity, and we know quantum mechanics is true by what we have seen in atomic physics. So there should be a resolution to this. And string theory offers a solution to this problem, and it gives us a consistent framework which unifies quantum theory, which describes the micro world, with Einstein's theory of gravity, which describes the macro world, into a which is a highly non-trivial accomplishment. It basically involves replacing particles, which are point-like, by extended objects like one-dimensional objects like strings, or even perhaps higher dimensional objects. One of the features that string theory requires are the existence of extra dimensions. Beyond the 3 spatial dimension and 1 time that we have, we need extra dimensions. Now, if there are these extra dimensions, it raises the questions, where are they? Why don't we see them? And the only resolution for that would be if they are tiny enough for it to be difficult to see them in experiment. But if they are tiny, how big are they? So first of all, we think about some of the dimension as being curled up. Like, instead of being long along some direction, they're kind of like circular in a tiny, tiny kind of region. And if it's sufficiently small, we cannot see it. We only see the long directions. And those are 3 long directions. The tiny directions that we don't see easily, which are tiny, the strings could wrap around them in particular ways, or different configurations that they can have. And from our perspective down here in the macroscopic world, where we have 3 big dimensions, they could look like particles of different properties. So different kind of strings would look like different kind of particles to us. And depending on what shape or what geometry we choose, we get different kind of physics down here. So the observed physics, like the particles we have, the things like electron, quarks, that all these elementary particles that we observe, their property will all be dictated by precisely what we are picking as this tiny little space. Each choice gives you a different 4-dimensional, 3 plus 1-dimensional physics. What is this exactly internal space, this tiny space which is compact and curled up? We don't know. It could have very complicated shape, and it has a lot of dimensions. For example, in the context of 10-dimensional string theory, we have 6 extra spatial dimensions, which is going to be even difficult to draw clearly. And the physical properties will be dictated by them. And hopefully, we believe, our observed universe corresponds to precisely one of these choices. Well, the question is, can this lead to any predictions for our universe? That's a big question. Are there restrictions to what can arise from different choices of tiny spaces? Could this lead to some predictions about the cosmology of our universe? Can this tell us something about the future of our universe? Our universe has some peculiar properties. The things we are made of are very tiny in mass. Things like electrons, quarks, which make up protons, are very light compared to the fundamental scale in physics. Why is that? Why are we made of almost massless things? Another feature of our universe which is very peculiar is dark energy. There's a very tiny energy which is all over the space, everywhere. And we don't understand why, or its precise nature. Also, dark matter is most of the matter in our universe. And we don't know what it is. The matter we are made of is a small minority of the matter in the universe. Quarks, electrons, and all that in the whole universe is a tiny fraction of the matter. Most of the matter is in the form of what we don't know. We call it dark matter. These are peculiar features of our universe. Can we have any insight into these kind of questions? Going back to the original line of thought, we can ask, can any imaginable universe with a prescribed set of particles and forces occur by choice of tiny compact space? Can you get anything you want? Or can we have, for example, a very heavy electron instead of very light ones? Can we have a universe with no matter at all? Can every matter structure occur in some universe? Maybe not ours, but in some other universe. Or the universe we know started with some kind of explosion and it's growing, expanding, Big Bang. Will our universe end? Is there an end to this story? Based on a large set of examples driven from string theory, the lessons we have learned from string theory, we know that there are severe restrictions on what we can get and what are the possible things that can emerge as particles and physics that we can observe. And these ideas, the restrictions that we get, can be partially explained from the consistency of black holes that Juan so nicely summarized in his talk. The mysteries of black holes, some aspects of it we think we understand, and those aspects already give us some insights about what can or cannot occur as possibly consistent theories when you combine quantum theory with gravity. And in particular, black holes, as was reviewed, has internal structures that have entropy, and they have thermal properties and gradually evaporate, and this consistency of their evaporation gives us severe restrictions of what can appear. Some novel requirements emerge. I will just give you some examples of them. For example, gravitational force is always the weakest force. In our universe, gravity is the weakest force. We have other forces like electric forces. So if you have two electrons, they repel each other much stronger than they pull each other by gravitational force together. So gravity is much weaker than the electric repulsion. And that's not only true in our universe, but in any conceivable universe, we think that's true. That whenever you have these electric fields, you have some charged things like electrons, for which the electric field is much stronger than gravity. Dark energy, if it is present in some universe, it should be possible to vary. It doesn't have to be constant. It doesn't have to be constant. It cannot be just a constant, or it at least has the potential of varying in space. And moreover, no theory with dark energy can be stable. If you have dark energy in a universe, it's in some sense bad news, in the sense that that universe cannot last forever. These are some of the two lessons we have learned. The third one is that if physical parameters are extremely small or large, extremeness in parameters in physics tell you that you must have some light particles around. The tower of them, not just one, a huge number of them, a tower of them, which are light. These are some of the lessons we have learned from string theory when we combine quantum theory with gravity. And there are many more. So what are the consequences of some of these for our universe? Well, as I mentioned, gravity is always the weakest force, which follows from, again, properties of the black holes and the fact that they decay. This already tells you some aspects of some restriction on the masses of the charged particles. And in particular, if you study this in the context of our universe, which has also dark energy, which I denote by the symbol lambda, it tells you that the mass is restricted between some power of the charge and between the charge and some power of the dark energy. So for example, for our universe, it tells you that the mass of the electron in fundamental units is between 0.1 and 10 to the minus 31. This is not a very strong prediction because it is, it's a wide range, but still is a prediction, and it agrees with not only the mass of the electron, but also the mass of the charged particles, the fundamental particles that we have, which is in this kind of range, 10 to the minus 22 and 10 to the minus 16 range. So the other prediction is the dark energy in our universe. We know that our universe has dark energy, and it's positive energy. We don't know exactly its nature, but we know that no matter how you get it, for example, if you have something like a potential whose minimum could be, for example, a positive energy, we know that this cannot be stable because we know far away, we have understanding that it has to decay to zero, the potential, and therefore it should be possible for the state that we are here to decay away and lose energy to go down to zero. In other words, anytime you have positive energy, since zero energy is always allowed far away, you're not going to be stable. It's possible to disappear and get rid of that energy. So it is unstable or metastable. We do not know exactly what's this rate. We know it's going to decay. We believe so. The rate we don't know, and it's still being debated. And some ideas suggest that it could be as low as 10 to 100 times the age of the present universe. The next thing we have observed in string theory that extreme parameters demand having light particles. So what are the physical parameters? Well, physical parameters could involve like constants which describe the electric charge and this and that. And one of the parameters in the theory is exactly this dark energy. The dark energy in our universe is very tiny. In fact, it turns out to be 10 to the minus 122 in fundamental units in physics, which means if you write 0.00, you have to have 122 zeros before you put a 1. It is a really tiny number. So this is perhaps the smallest non-zero tiny number which has been measured in physics. So it's an extreme situation. And the ideas that we have from other aspects of string theory suggest this must be related to existence of some tower of particles whose mass scaled with some power of this dark energy, lambda to some power. And combined with other observations, it suggests that this power is 1/4. And this suggests that then the question is, what is this light tower? What does this mean? What are these particles? What property do they have? This idea suggests that there should be exactly one extra dimension whose length scale is related to this dark energy, to the minus 1/4, which give you a scale of the order of 1 micron, which is 0.001 millimeters, a thousandth of a millimeter. So the idea from extreme parameter that we have the dark energy predicts a scale which would be this one extra dimension of this size. And this suggests that Newton's gravitational attraction, which goes like 1/r², should become 1/r³ if you go to a distance smaller than this scale. Now, currently the measurement has been done to about 30 microns or so, and the Newton's law holds up to 1/r². And so they are actually being tested now. What happens if you go further than that? And in fact, they believe they can push it down at least to 10 microns and perhaps even smaller in the near future. So this is quite exciting potential observational imprint of this idea. And then the question is, we have said there are these light towers. Have we seen this light tower of particles? Indeed, we think we may have. This tower of light particles naturally fit with the properties we expect of dark matter. So we say, what is a dark matter? Well, I'm saying there's a dark energy which demands light particles. Well, these light particles could constitute precisely this dark matter that we are missing. It has the right properties to be exactly the dark matter because they interact very weakly, and it has all the properties that the dark matter needs to have. So this leads to certain predictions for the structure formation which are being studied right now, this picture of this dark matter. Anyhow, in conclusion, there are exciting connections between large distance predictions from fundamental consistency of the theory at the smallest distance scale. To have a quantum gravity at the small distance, quantum aspects predict something at the large scale, like the dark energy and properties of that could be potentially tested in experiments. And the consistency of quantum theory of gravity as represented by string theory can lead to non-trivial and testable predictions for our universe, some which are being carried out today. Thank you. Shukran.
It's really a tremendous pleasure to be here. It's a very beautiful country, and I'm thrilled that such exciting physics is happening here. Oh, so I have to get where's my talk here? Da-da-da. I think that's me. Very good. Okay. sorry. How do I, and can I make this full screen here somehow? No? Oh, here, maybe up here. There we go. Okay. All right. So, one of the really wonderful things about fundamental physics is that we ask incredibly simple questions about the universe around us. And if we ask these questions and we keep asking why over and over and over again, we inevitably run into the very frontiers of our understanding of the laws of nature today, with deep mysteries surrounding us in all possible directions. And that's what I want to talk to you about today in the context of an incredibly simple, obvious seeming fact about the world. The universe is big. Okay? So almost all of you have probably seen some version of this picture of all the scales in nature. And actually, these are all the scales that we have sort of probed observationally, experimentally, one way or another. From the very largest distance scales, around 10 to the 28 centimeters, that's about the size of the observable universe, all the way down to distances around 1,000 times smaller than the nucleus of the atom, which we're probing at very large accelerators. Okay, so, and it's really incredible that in almost every decade of length scale between these two extremes, something exciting is happening. So we have galaxies are around 1 million times smaller than the universe. We have the solar system. People are somewhere here in the middle. Atoms are around 10 to the minus 8 centimeters big. The nucleus of the atom, protons and neutrons, are around 10 to the minus 14 centimeters big. Okay, so there's this huge range. So why do I say the universe is big? Well, obviously the universe up here is way, way bigger than all these tiny things down there, and we're going to spend a lot more time talking about that. These also represent the extremes of what we care about experimentally in fundamental physics. At the very smallest distances are being probed at the Large Hadron Collider, around this 10 to the minus 17 centimeters, 1,000 times smaller than the nucleus of the atom, and at the very largest distances by various cosmological observations. So let me try to make a little bit more precise the sense in which the universe is big. Well, you know that all matter is made out of atoms. Here's a typical picture of an atom is some electrons going around protons and neutrons. So this is maybe a hydrogen atom. If we zoom in on the proton, we've known for a long, long time that the protons are not actually elementary particles. They're made up out of other stuff. They're kind of a messy, complicated bag that has these wonderful objects called quarks inside them that are held together with gluons. So that's what we get when we zoom in on the proton. The electron, though, is zooming around the proton. And as far as we know, the most powerful microscopes that we've used using these giant accelerators, these underlying elementary particles, the quarks and the electrons, are point-like. As far as we can tell, they don't show any substructure, any size of any sort at all. Okay? Now, here's the question, could that keep on going forever? Is it possible to have really perfect exact points? And this is the first thing that's going to establish our sort of metric, our yardstick for how small is small, is that there's actually a limit to how small is small. There's kind of a smallest possible distance at which it even makes sense to talk about points in space and time. Right, and here's a little thought experiment that you can do. This is I'm a terrible artist, so this is supposed to be a magnifying glass. So suppose you're using a magnifying glass to probe shorter and shorter distances, okay? Because of quantum mechanics, to probe shorter and shorter distances, you need higher and higher energies. You need shorter and shorter wavelengths. The shorter and shorter wavelengths have higher and higher frequencies, and therefore they have higher and higher energies because of quantum mechanics. This is the ironic reason why the machines that we use to probe the very smallest distances humanity has ever probed are the very biggest machines that humanity has ever made, like the Large Hadron Collider, right? It's because of this basic reason. But in a world without gravity, there's no problem if you ask for more and more billions of dollars from more and more multinational organizations to go arbitrarily short. However, when you have gravity, something very bad happens. At some point, you put so much energy into such a tiny region of space that, as Wan and Cameron reviewed, what happens when you put a huge amount of energy into a tiny amount of space? You make a black hole. Okay? And that obstructs your ability to see what was going on in there. And let's say you get frustrated and say, I'm going to use an even more powerful magnifying glass. What happens? You make an even bigger black hole. Okay? So there's no way, even in principle, to probe arbitrarily short distances and times. And the length scale and time scale at which this happens is this ridiculously tiny but very fundamental length scale known as the Planck scale. 10 to the minus 33 centimeters, 10 to the minus 43 seconds, which is how long it takes light to traverse this distance of around 10 to the minus 33 centimeters. And that's some ultimate yardstick. Okay? That's some ultimate short distance scale beyond which even the notion of distance doesn't make any sense. But relative to that, everything in the universe is just gargantuan. Okay? So there's this sort of one natural scale that's just handed to us by the laws of nature. Everything else is enormous compared to that. Something else that we learn from this, which has been alluded to in various ways in the previous two talks, is that the very notion of space and time themselves are likely approximate. We can't even in principle give them an operational meaning. And whenever that's happened to us in physics before, when it's become impossible to give some notion, even in principle, an operational meaning, we've eventually discovered that that notion had to be replaced by something deeper. In this case, it's very shocking that the thing that has to be replaced by something deeper is space and time itself. So if we go back to the previous picture and sort of clean it up the way a fundamental physicist would do, so all the exciting stuff in the universe, the galaxies, people, all that stuff is gone. So we have the very largest scale, around 10 to the 28 centimeters, the size of the observable universe. This is the length scale, something very important that happens there. In a different talk, I would spend longer talking about it, but this is actually another fundamental length scale that's associated with the range over which the subnuclear forces that give rise to radioactivity act. That's why it's called the weak scale associated with weak interactions. And I've now put down this third length scale that we learned about, the Planck scale. And this picture actually has some dramatic mysteries associated with it that we're going to talk about in the rest of this talk. So why are these separations so enormous? Okay, why is the universe 60 orders of magnitude bigger than the Planck scale? Why is the weak scale 16 orders of magnitude bigger than the Planck scale? Why is there a macroscopic universe? Okay, why is the universe big? Now, you may think, well, it is what it is. It's just some number. You know, why are elephants big? Okay, they're just made out of a lot of stuff. It's not a question. But we're going to see in the rest of the talk why this is a question and why it's a mystery. And to do that, I'm going to do something very dangerous in a public talk. Okay, I'm actually going to try to explain something, right? Okay, so this is very dangerous, but I'm only going to use physics that I hope you vaguely remember from high school, except unless you're a high school student, in which case there's a homework problem for you in 3 slides. Okay. All right, so we're going to talk about units. I'm going to try to explain a little bit more detail, again, this difference between big and small. If you ever encounter physics at any level, the units are the bane of your existence. There's so many of them, it's impossible to remember all of them. I certainly hated units when I was learning physics, and I loved physics, okay? And it's something you learn in physics is every time something sucks in physics, it's a fault of human beings, okay? Because human beings have decided to interfere and make stuff up, whereas you should just ask nature for things and not have arbitrary human constructs. Units are a great example. So let's say that you had a friend on Mars, and you wanted to explain to them how tall you were, right? So you say, I don't know, I'm 1.5 meters tall, 1.8 meters tall. Okay, you're talking to them on the phone. They say, great, what's a meter? They're like, oh, well, there's this bar in Paris. Well, that was the answer a long time ago. But anyway, there's a bar in Paris, and what it means to say I'm 2 meters tall, which I'm not, but what it would mean is if you take 2 of those bars and lay them end to end, they would be the size of me. But they can't get to that bar in Paris. They have no idea what you're talking about. That's a totally useless way of telling them how tall you are. How should you tell them how tall you are? Well, you should talk about something that's the same on Mars as it is on Earth. And for example, that's the size of a proton. Okay? So protons are the same on the Mars on Earth, and I could tell them instead that I'm around 10 to the 16 protons high, right? And then they would know what I'm talking about, okay? All right, now, and in fact, we can do this. It's a very beautiful thing that because we have these 2 fundamental constants, the speed of light and Planck's constant in quantum mechanics, we can actually convert all units in the world to just 1 unit. And we can choose that to be a unit of mass or energy or length or time, it doesn't matter, but we can convert between all of them. So for example, you can convert a time to a distance. We're all familiar with this. We say, 1 light year, or 3 times 10 to the 8 meters. Those are the same thing, right? And we use the speed of light to convert between them. Slightly less familiar, we can use Planck's constant to convert between an energy and 1 over a time. Okay, so, and so in this way, all units can be related to just 1. And particle physicists tend to use it as a unit of mass or energy, which is around 1 gigaelectron volt, which happens to happily be around the mass of the proton, the mc squared energy or mass of the proton. All right, so we can convert everything to this. So this is, I mentioned before, that I'm around 10 to the 16 protons high. If I told the person on Mars that my mass is 10 to the 29 GeV, they've learned something. I've made out around 10 to the 29 protons. That's great. If you're very lucky, the rest of this lecture will last around 10 to the 27 inverse GeV, which is the amount of time it takes light to travel the size of a proton. Okay? Now, and again, the size of a proton is around 1 over its mass, 1 over a GeV. The energies of the Large Hadron Collider are around 7,000 times the rest mass of the proton and so on. Now, the wonderful thing with working in these units is that, first of all, you don't have to remember all those stupid SI units anymore. Everything is completely natural and is determined by nature. I guess it's the definition of natural. But we learned some pretty dramatic things right away. So you all probably, hopefully remember from high school that the electric force between a pair of electrons goes like the product of their charges divided by 1 over r squared. Okay, just like the inverse square law for gravity, which we'll come back to in a second. Well, if you just use the rules that I told you, this is one of the high school exercises, then you discover that the electric force, the force, already has units of 1 over length squared. And that means that whatever multiplies it is actually just a pure dimensionless number. That's amazing, that the electric force is associated with a pure number that happens to be a small number. It's called the fine structure constant, and it's around 1 over 137. That means in a very specific, concrete sense, the electric force is weak. It's a small number associated with it. Okay? On the other hand, you see gravity is not like that. If you remember your formula for the gravity force, it's Newton's constant times the product of masses over r squared. And that tells you that Newton's constant times the product of masses is dimensionless. But that means that Newton's constant itself has units. And in fact, Newton's constant has units of length squared. It has to make up for the units of the mass squared there. It has units of length squared. And in these units, in these natural units, G Newton is in fact precisely this famous Planck length squared. Okay, so one way of saying why this length scale is so minuscule is that it's a reflection of how minuscule gravity is in strength compared to the other forces. So let's talk about this comparison. It's been alluded to a couple of times already. So if I take the electric force between 2 of the protons in a hydrogen atom, of course the whole hydrogen atom is neutral, so the net force it cancels out. But if I just look at the part between 2 protons, okay, and I compare that to the gravitational attraction between them, they both go like 1 over r squared, so that canceled out. But the gravity part has G Newton times m proton squared. The electric part just has that q squared that we just talked about. This number is 10 to the minus 38. That number is 10 to the minus 2. So the ratio of these forces is 10 to the minus 36. The whopping 0 with the 35 zeros and then a 1. Okay, gravity is ludicrously weak compared to all the other forces. Another way of seeing it is that, there, I just picked that up. The entire mass of the Earth was pulling down on this, but did not stop me from picking it up. Okay, so now, we're going to ask the question, why is the universe big? But I'm going to ask a slightly more familiar question first. Why does a big universe have big things in it? Like you and I are big compared to atoms. Why is that? The Earth is big compared to atoms. Why is that? We're going to first see that the answer to this question, why the universe has big things in it, is exactly the question, why is gravity so weak, is exactly the question of why are particle masses so minuscule compared to this Planck scale that we talked about. So for instance, you might think, if you look at all the rocky planets in the solar system, they all have roughly the same size, within a factor of 2 or 3. And that's not an accident. There is a kind of a maximum size that you can make rocks before what happens, that the gravitational attraction that wants to crush it is being balanced by the sort of atomic pressures that want to keep it from being crushed. And rocky planets are about as big as they can get for those two pressures to balance against each other. This is one of the exercises for high school students, is to actually do this estimate, to look at what is the gravitational pressure that would want to crush the Earth and compare it to atomic pressures. And you find, without even putting in any numbers, that there's a formula that the size of the Earth is bigger than the size of the atom by exactly this factor we saw here, exactly this ratio, exactly this formula, this combination shows up. And you find that it's actually raised to the 1/2 power. The Earth is bigger than atoms by precisely the degree to which gravity is weaker than the electric force. And you can put in the numbers and see that it works. The size of the atom is around 10 to the minus 8 centimeters. That ratio is around 10 to the 18, and indeed the size of the Earth is about 10 to the 10 centimeters. It's about right. Another exercise for high school students, repeat this exercise for elephants, okay? There's a difference between the size of elephants and the Earth. I'll just give you a clue. For the Earth, you don't mind if you sort of crush the entire molten core of the Earth. With the elephant, it's not so good if you crush it all into one big glob of goo. You want to make sure that you don't crush the sort of bones on the planes in its legs. And if you just carry through exactly the same exercise, you find essentially exactly the same formula. But this 1/2 power here gets replaced by a 1/3 power of the ratio of the strengths of the forces. And it also works. The size of the elephant is around 10 to the 4 centimeters. This ratio is around 10 to the 12 times bigger than the size of the atom. Okay? So I hope you see from here, the reason the universe has big things in it is precisely the degree to which gravity is weak. What would happen if gravity got a lot stronger? You and I would all be crushed into teeny tiny, unfeeling black holes. Okay? There'd be no love, it would be a disaster. Okay? All right, so now I want to switch to the second question, in fact, even the more dramatic question that will then allow us to segue into why this is such a mystery to begin with. Why is the universe big? The universe itself big. And this is the essential origin has to do with this fact that because of both relativity and quantum mechanics, we've known for a long time that the vacuum is exciting. If I go back to my crappy magnifying glass, if you actually look at a little region of space and time, the amount of energy that you put into that region, just to do the looking, has the ability to produce particles and antiparticles that pop in and out of the vacuum. Okay? And so the vacuum you should think of as this roiling mess of particles and antiparticles that are fluctuating more and more violently the shorter and shorter distances you will look at. And in fact, the vacuum is too exciting. And it's because even vacuum states, even the lowest possible energy states that you can have in quantum mechanics have some energy. This is again a consequence of the uncertainty principle. If you imagine you have a pendulum, the physicist's favorite toy, because we haven't developed since the 1700s, okay? So if you have a pendulum sitting there, in a classical world you could say that it's at the bottom and that it's not moving. But quantum mechanically you can't both know that it's at the bottom and that it's not moving. So there's an inevitable amount of jitter associated with it, and that gives a minimum amount of energy associated with it, which is the famous Planck's constant multiplied by the frequency of the oscillation. Now let's go back to our picture of these vacuum fluctuations, okay? And the problem is that in any size box, you can have some sort of, some wavelengths of the typical size of the box that are fluctuating in and out. They have some energy associated with their frequency, but what happens is you make the box smaller? Everything gets worse, right? The wavelengths get smaller, the frequencies get bigger, the box gets smaller, so the amount of energy per volume is just going through the roof. In fact, naively, the amount of energy per unit volume that's just contained in these quantum mechanical fluctuations of the vacuum would be infinite. But remember, we just said we can't really talk about things less than the Planck length, right? Space and time is breaking down. Everything is like going to hell near the Planck length. But we can sort of do an estimate somewhere around the Planck length to get an idea of how much energy there should be in the vacuum. The amount of energy in the vacuum, this has a name. It's known as the cosmological constant, lambda. Kamran referred to it in his talk. Well, we can do an estimate for this. The vacuum energy density is the energy over a volume, and that's going to be the Planck energy per a Planck volume. And now comes the difficulty that Einstein told us that every form of energy gravitates. It curves space and time. This is a form of energy that's uniform everywhere in space. So it should be curving space-time uniformly everywhere in space and time. And what does it do? Well, you don't need to know any formulas, because the only word that occurs on this page is Planck. Planck, Planck, Planck. Okay, so all that can happen is that there's a curvature in space of order the Planck scale. So you could curl up the universe to be teeny tiny on scales of order the Planck scale, or it could be explosively accelerating, doubling in size every 10 to the minus 43 seconds. Now, that's wrong. That's not what the universe looks like. It's not doubling in size every 10 to the minus 43 seconds. So what we do is we say that the actual observed value of the energy of the vacuum happens to be this quantum mechanical piece that I just told you about, plus some classical piece that was sitting there already. And one of them, if you calculate it, this one you tell your graduate students to calculate, you find in some units is 2.6493781, blah, 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 120 decimal places. You say, thank you very much. That means that the classical value had to be negative of that one, but it starts differing in the 121st decimal place. That's what we literally do. Okay? And it's not inconsistent, but it makes you think that it's probably not the right answer either. It's like walking into a room and seeing a pencil standing on its tip, balanced to within 10 to the minus 120 degrees of vertical. That could be, but if you saw it, you'd probably wonder, there's something up. Is there a string? It's hanging from the ceiling? What? There's probably something going on, right? There's a very similar issue associated with why the elementary particle masses are so small compared to the Planck scale. And this would be a whole other talk, and I'm already over time, be a whole other talk to explain that our current understanding of where the elementary particle masses come from is that there's a sort of Higgs field that fills all of space, and that roughly the particles, like the electrons, as they move around, every 10 to the minus 17 centimeters or so, they bang into the Higgs. And that's what gives them inertia. That's what gives them mass. But the Higgs itself should have these violent quantum mechanical fluctuations. It should be fluctuating back and forth on the Planck length as well, and that would make the electron 17 orders of magnitude, 16 orders of magnitude heavier than it is. And that would crush all of us into black holes. Exactly the same issue of the violence of the quantum mechanical fluctuations shows up here. So, in other words, if we didn't do these crazy adjustments of the parameters, instead of having this huge separation between these scales, they would all be on top of each other. This would be an incredibly unpleasant universe. And so we are left with the question, what controls the violent fluctuations of the vacuum? Why is the universe big with big things in it? And I really am out of time. So this is really the place to end. We don't know. Okay?
Let me invite all the speakers back up. Okay, so you didn't tell us why is it so big?
Well, you're not going to let, okay. I'll just say that there have been, for a long, long time, people, at least for one of these problems, for why the universe has big things in it, the character of explanation they're looking for was like the string, the pencil is hanging from a string from the ceiling. Or really better, if you look carefully, you see there's a tiny hand that's holding up the pencil. There's some mechanism that shows up that really stabilizes, removes these violent quantum mechanical fluctuations. If such a mechanism were to exist for the case of why the elementary particle masses are small, we should have seen it in experiments at the Large Hadron Collider. A lot of people expected to see it, we have not seen it. So that's a sort of blow from nature over maybe we'll still see it, but it seems very unlikely now. The other, the question of why the universe is big, why the vacuum energy, the cosmological constant is small, that for a long time has been clear there can't be some analogous something removes the fluctuations mechanism. If there was, it would have to operate, the universe is so big that the relevant length scale would easily be macroscopic and we would have noticed it. We would, if something like that was going on, we'd see something at the sort of millimeter scale that Kamran was talking about, and we have not seen that.
Okay, let me ask this question to Kamran. Are there effects in string theory that might explain this?
Yes, there are some aspects in string theory that hint at a possible solution to this question, which is we know that the ideas that leads to the computation that Nima was referring is what we call the field theories. And as I was saying, in the context of quantum gravity, we know aspects of field theory don't work the way we think. A simple example is that when we do computation in string theory, the naive computation that the field theory will do will give you vacuum energies, which is of the order of Planck. Whereas string theory cuts it off at a much smaller scale, at the string scale, which for weak coupling is very, very small compared to that energy. So the naive calculation that we would do in a field theory would disagree with the calculation we already know how to do in string theory. So that's an example where it's hard to explain in the language of field theory, but we know how it works in the context of string theory. So it seems one possible solution would be that the kind of calculation that we need to understand is the objects that we think are fundamental would be viewed as composite of a light thing, and that light thing sets a scale, which indeed would be the dark energy. That's one possible picture that these pictures suggest.
I have 3 slides at the end of my talk, and actually the last slide was a picture of a snake eating its tail, which is more or less what you're saying.
Yes.
It's possible that this question of where space and time emerges, that Swan told us might have something to do with quantum information. Kamran was talking about string theory. In any case, there's some more fundamental rubric out of which space-time emerges. It's very possible that that's related to why the space-time that emerges is big, right? That those questions might not be unrelated to each other. And many of the attempts over the past 30, 40 years have treated these questions as both important but essentially separate.
Juan, my next question is to you. So you said that there's an assumption that a black hole can be thought of as a collection of qubits. But you also said that a black hole is kind of like the time reverse of a Big Bang. Is there a similar assumption about equating the Big Bang to a certain number of qubits?
Yeah, so there maybe. So there are certain ideas that an expanding universe, as I said, will also have a horizon that would have, if it has constant expansion rate, it would have finite size. So in fact, our universe is now entering a stage where it will have a constant expansion rate in the foreseeable future, probably. And so the Hubble scale would be our horizon. And then the idea is that that universe would be described perhaps by a system of qubits. And we need that number 10 to the 120, the same number that appeared in Nima's talk, of qubits to describe. But there we don't have any example. So in the case of black holes, we have at least toy models of systems that can work. In this other case, it's a little less clear. But maybe it's true also in that case. And that might be one of the lessons that black holes might teach us about cosmology.
Then it's interesting why your universe needs such a gargantuan number of states to describe.
Right.
You know, you and I would be perfectly happy with 10 to the 50. You know.
Yeah, I think one difference between black holes and the universe is that black holes, you might assemble them from the outside. You have the choice of how much matter you send in and so on. On the other hand, the universe is something that self-assembles. And so I think it has one more degree of complication that we haven't understood.
Kamran, you had some work on one example from string theory for what these qubits are that describe black holes, some structure for black holes. Can you tell us a bit more about that?
Right, you're referring to the work with Andy Strominger, I believe. So we were trying to find examples in string theory. This is just after what we call this duality revolution in string theory in 1990, what was it, 4 or 5, and the developments of some objects that we understood were important. With my colleague Andy Strominger, we were trying to find examples in string theory where we could explain what is black hole made of To do that, we had to make a black hole using string theoretic objects. So string theory is made of these, these extended objects like strings and membranes and this and that. And so we thought that it would be a good idea to try to make a black hole made of these wrapped around the extra dimensions in some funny ways. And we said, well, perhaps if we count how many ways these things can wrap around these extra dimensions, that different ways could correspond to different degrees of freedom of a black hole. So the calculating of degrees of freedom or entropy of a black hole became the question of finding ways to wrap these membranes or strings around these tiny spaces. So in this way, two problems got solved in the following way. One was the question of who needs the extra dimensions of string theory? What are they good for? And the second question was, where are the internal degrees of freedom of the black hole? What are they made of? So these two questions became one each other's answer. So the extra dimensions of string theory became the place to wrap around and give these extra degrees of freedom of the black hole.
Mm-hmm. I see. One last question to Juan. So you, no, actually this was to Nima. So you mentioned this phrase, thought experiment. What does that mean and how costly is it?
It's for people funding theoretical physicists, it costs zero, and I think probably thought experiments have had a greater impact on humanity than many real experiments. Maybe as a theoretical physicist, I might say than all real experiments.
You're not biased at all.
But I'm not biased at all. But maybe I can make maybe a general point, because people do ask us this question all the time. Oh, what you guys are doing is esoteric, has nothing to do with real life, etc. Whereas people who work in fundamental physics don't feel this way at all. We don't feel our questions are esoteric. They're about the most basic things about the world that we see and experience around us. And 100 years ago, a little over 100 years ago, there were a bunch of eggheads who were studying ordinary matter, right? What's going on with ordinary matter around us? Why do they exist? Why do they make sense? Things that you would just take for granted, not even as something to be explained. Well, it turned out to try to understand why ordinary matter was the way it was, ended up revolutionizing our understanding of nature and eventually, ultimately, revolutionizing technology as well. And today, there are these extremely basic questions about things that we even take more for granted. The space and time that we move in, the fact that it's big enough for us to be able to move in it. These are similarly profound questions, and I'm not guaranteeing that if we answer them, we'll make similarly dramatic impacts on our lives, but this strategy has worked before.
Mm-hmm. Okay, so I think for the next 10 to 27 protons, I think?
Yes.
Yeah, we'll open it up for questions. So just raise your hand and somebody will bring you the mic. It's down here.
Yeah, hi. Nima, I saw one of your talks on YouTube, and you were talking about...
I'm sorry, then.
And you were talking about stripping the universe from space-time by going even more fundamental. Can you elaborate on that? Because I was hoping to hear more about this today.
Well, I mean, today I wanted to talk about things that we really know are true. I mean, at least we know what the mysteries are, and it's possible to explain. But yeah, there's many aspects of this general challenge of trying to understand how to make do with physics if we're going to eventually lose the concepts of space-time. And one strategy is to try to, if you think that's going to happen, to try to reconceptualize ordinary physics where you think you need the concept of space and time kind of with one hand behind your back, not using concepts of space and time so explicitly. So that's one line of work that a few of my friends and I have been pursuing for the past decade or so.
Thank you very much for the very interesting short talks. I have a question on quantum gravity, really. So if I look at gravity, it started with an idea, right? An idea that if you fall in free space, then you feel nothing. And that led Einstein, after 10 years or so, to general relativity. And the idea in quantum mechanics is really that everything that can happen does happen, right? And it took Feynman and a few others maybe 20, 30 years, of quantum mechanical development to figure that out. So it's a super basic idea that leads to this theory. So in my mind, there must be a super simple idea that underpins quantum gravity, right? And then you could say that's maybe string theory, which everyone had hoped, right? Super simple idea, it's not a point, it's a circle or a membrane. But you know, the brightest minds have been working for 50 years and found nothing. So are we missing something? Is there, you know, what is the basic idea that can lead us to more insights in quantum gravity? Are there other ideas?
So maybe I can say. So, well, I would say that certainly string has led to a lot of progress in the past 50 years. It's true that we certainly haven't gotten to the bottom of it, if that's what you mean. That's for sure I agree with. But to say that we haven't learned, it's, I think, perhaps an exaggeration in the other direction. I think we have a lot of the progress we have made in theoretical physics is because of the ideas that we learned through string theory. However, it is true that we haven't been able to nucleate that lesson into simple rule. And I agree with you that we expect the answer to be simple at the end. It cannot be a hodgepodge of rules. It should be something relatively simple to understand. However, we know why it's not simple to understand yet. And we know it because what happens, unlike the usual things about particles, in particles we think that when you go to smaller and smaller scales, you get to a simpler thing, and it stops being more complicated after a certain scale. In gravity, we know that's not true. That we know that when you get smaller and smaller, after you pass these lengths that both Juan and Nima talked about, 10 to the minus 33 centimeters, you cannot get any smaller. And indeed, if you try to, you get things more complicated. That there will be more complication, that the energy needed will be actually more complication. So therefore, that means that there is no reduction to the simplest ingredient that we hope. So this connection between small scale and large scale, this mixture, is what is at the heart of difficulty of giving a simple formulation of quantum gravity. We think that the small and large talk to each other. Short distance and long distance are not separable, and that's a big difficulty. But of course, we ultimately hope that there would be a way to put this together, but it's going to be something very different from the way we have been thinking about quantum field theories.
Can I make just a short philosophical comment, which is that these very simple sounding principles only look simple after you've understood everything, and that you can tell a very clean story. You know, it does, I think, a lot of disservice to Einstein to say that, well, he had this great idea that you don't feel your weight, and then you're done, right? He's an idiot that he worked another 10 years after that? He's not an idiot, right? That there are a lot of people who could have had that idea. I can actually tell you the secret. I discovered myself as a high school student the principle of equivalence. I've probably heard of it. But anyway, I certainly could not figure out how to turn it into a theory of gravity. I think probably many people had this idea that gravity and acceleration are the same thing, but it was a tortuous journey filled with all kinds of, the problem is it's not enough to know the things that are right, you have to know why all the wrong things are wrong. And that's the truly difficult part of the journey of a theoretical physicist. So I don't think it's, until we get to the bottom of it, we don't know. It's very important to have slogans to sort of keep you going. It might be this, it might be that. But until we get to the bottom of it, I don't think we know.
Question over there?
So I have a two-part question. So the first question is, if the universe is expanding, what is it expanding into? Like, is there a pre-existing space outside the observable universe that the universe is expanding into? And my second question is, if I go to the very edge of the universe and reach my hand out, what will I feel like? Or like, can I poke outside of it? Or like, will I go in circles? Thank you.
Who should answer this?
Well, I think we only talk about the intrinsic geometry of the universe, so it's not expanding into anything else. I mean, you could embed our universe into a bigger thing mathematically, but we think that for determining the laws of physics and your experiences and so on, it's enough to talk about just the geometry of the universe. Just distances are getting larger between, you know, two points or two free particles. They are getting larger and larger, and space is being created, but not into anything. So that's one thing. The second is we sometimes say that the expanding universe has a horizon, right? Now, if you go to that place where the horizon would be for us, then I would just cease to see you. But you would be perfectly fine, right? So you extend your hand, and it would be like you were here. But I would stop seeing you once you go behind the horizon. That's how we think our cosmological horizon works. Now, it could be that if you travel further and further, the universe starts looking more and more different. And that's another theory of the multi-universes and so on.
And it could be that you come back to yourself.
Yeah, that also.
It could be that if you go that way, you come back this way. We don't know if that's impossible.
You can't get away. Just wait for the mic. It's right here.
Sasha Migdal, Adia, and NYU Abu Dhabi. Hi. Look, for the last 20 or 30 years, I switched from quantum field theory to classical theory and finance. And I have a kind of broad perspective. And I look back on the problems of quantum field theory. So both in classical physics and finance, there is such a notion as stochastic differential equations, equations with artificial random noise. And it is known that quantum field theory also can be reproduced as a stochastic quantization when you have some classical equation and artificial noise. Now, what if, in fact, there is some nonlinear equation with natural noise? And that natural noise happens at small scales, and at large scales, it imitates random noise and produces effectively quantum mechanics. In other words, my biggest questions to you guys is that maybe quantum mechanics is not absolute. Maybe it is too bold to extrapolate linearity of superposition principle all the way to Planck's scale. So maybe at Planck's scale, quantum mechanics is wrong. It is just linearization now. What we see may be linearization of some other theory. And one of these theories could be nonlinear differential equation with natural noise.
Who wants to take that?
Well, I guess the question is, so we have some observations. We have the laws of general relativity and quantum mechanics, and they could come from something else. And in principle, we have to guess something else that would give us these two things. And I think anyone is welcome to make their guess, and maybe it is stochastic differential equations that then give rise to quantum mechanics and so on. As far as I know, no one has made that work for consistent with relativity. Yeah. But yeah, it might be possible that both things are emergent, and it might, quite likely perhaps. Yeah. But our modus operandi has always been to assume both constraints somehow. String theory, for example, is a particular model we think about, and in this model, you can derive both things. You can derive gravity and quantum mechanics, and it's highly constrained. So there is no other idea, and many things are working with this model. Yeah. Maybe at some point we'll have to supplant it with a better model.
Yes. Related to this, I would say that many ideas, string theory has revolutionized many ideas in theoretical physics. We have learned a lot about theoretical physics. One thing it hasn't touched at all is the basic foundations of quantum mechanics. And I would agree with Sasha, surprisingly, that this has happened. I would have expected that since quantum mechanics has a lot of enigma in it, I would have thought that something should replace it, and string theory would be telling us what. But surprisingly, string theory is telling us the naive version of quantum mechanics seems to be valid in every way we know in string theory. So even though I sympathize with the question, the direction that quantum string theory is leading us is not in that direction, at least not yet.
Maybe I can add one thing that I don't think, Sasha certainly understands this, but I think a lot of people don't appreciate that having both quantum mechanics and relativity is just a ridiculously, shockingly restrictive straitjacket on your theoretical imagination for what might happen. And it's such a strong straitjacket that you can even sort of probe for what sort of little deformations might be. And it's very difficult. In fact, part of the reason why we haven't done what you're saying is that no one has even found a candidate possible even sort of parameterization of a deformation away from quantum mechanics in the situations where quantum mechanics gives us legal answers to legal questions, which doesn't violate the principles of relativity. If we didn't have relativity, well, we could have hidden variables, all kinds of crap could be going on. But having both quantum mechanics and relativity just seems to make it impossible to do that so far. It's a big gift. Right.
And relativity, they don't want to marry.
Well, so I very much sympathize that it's likely that they'll emerge together from something else. But yes, yeah.
I mean, they're present in our world, and
yeah, right.
So
they have to coexist, even if they don't marry.
Yeah. We don't want divorce. We don't want to be children of divorce. Yeah.
Maybe a technical answer. I wonder if what you're suggesting satisfies Bell's inequality or not. I suspect that it doesn't. Rather, it doesn't pass the Bell test.
Thank you very much for the nice talk. My question is more philosophical. Thank you. It's more philosophical, maybe. People were saying something like, okay, I reach to the end of the observable universe and I extend my hand and see what happens. And now I would like to ask, like, I go to the beginning of the universe and try to go a little bit further in the past, right? And this is something that I'm also a physicist, and it's always contrite me. And then, like, okay, either something started, and then from what did it start? Or this is like an infinite cycle of something that is repeating itself, or there are, like, I don't know, different theories of what can happen. And I would like to ask, like, do we have any hope of like really getting to some in the future some answer to the life cycle of the universe or the formation of the universe with respect to what happened before, or is our ape descendant human brain constrained to never give an intuition to that? Maybe you were mentioning things about formation of the universe and disappearance of space and time as foundational concepts, and I would like to hear the opinion of the masters in this philosophical point. Thank you very much.
Well, I think that the question of what happened before does not necessarily have to have an answer, in the following sense, that it could be that time ceases to make sense there, is replaced for something else which doesn't have a before. So that's one possibility. Another possibility is, of course, that there was something before, and we don't really understand it.
Well, related to that is that we have learned from string theory that one of the things that happens is that you don't have a complete description of physics in all ranges of parameters. We only have a little patch description. And what happens when you go to extreme limits, a new description takes over. So one thing that could happen is that when you take the universe back in time, you get to a situation where the description that we have of the universe today totally breaks down, like these light tower of particles I was referring to. Some new degrees of freedom come in to be much lighter than us and will reformulate us in terms that we are not familiar with. Maybe the dimensions change, maybe different properties take over. So it's a possibility that what you call as what was before would be a totally different universe, and we emerge from it. And only our part is describable by the physics we know today.
I think this is part of the fascination and challenge of fundamental physics, is that we've learned, certainly over the past, starting in the 20th century, aspects of it even before. It's a startling thing. Not every question that's framed in human natural language turns out to be a sensible question about nature. And we don't know ahead of time when that's going to happen to us. And that's why we have to have this sort of the spirit that the wonderful, famous theoretical physicist John Wheeler called radical conservatism, which is that you have to always be sort of mindful that the principles might have to be replaced by something radically different. But you can't stupidly just give them up one by one. You hold them on for dear life as long as you can, extrapolate them boldly into regimes where you haven't seen them work before, but until they scream out some internal inconsistency, you just keep on going. That strategy has worked, and that strategy has allowed us to overcome these like artificial ape brain problems you're referring to, the fact that human language questions don't necessarily make sense. By taking what we know, extrapolating, and finding the places where finally some inconsistency happens, we learn the new grammar, the new words, the new language. We've done it a number of times before, and we hope to do it again.
Take the final question from Mariette.
I hope you can hear me. Mariette Westerman. I want to thank you for staging such an extremely interesting and approachable discussion about theoretical physics and applying it at this extremely minuscule and gigantic scale to help us think about how we are in the world and how we can think about our place in the universe. It's very exciting. I am obviously, as I said, an amateur because I am an art historian, and I want to ask you, as theoretical physicists who also stand so clearly in the world, what prospects there are for observational astronomy, and particularly the James Webb Space Telescope, to illuminate the kind of questions that you have. Is there a place for observational astronomy and astrophysics at all to help illuminate these very difficult mathematical problems?
Maybe you can say one thing. In fact, this is where the art and science get together. You must have seen pictures from James Webb Telescope. Beautiful. They're almost like painting, drawing. It doesn't sound real. It's so beautiful in some ways. But actually, that's teaching us about fundamental physics. For example, we are learning that galaxies were much more numerous at the earlier time than we expected, and our theories don't seem to explain that correctly. So that very simple observation already is challenging the models we have of how the galaxy's structure formed at such an early time. So that's exactly an example where the Space Telescope and the images, which are all artistically beautiful, is shedding light on deep questions of fundamental physics, and physicists are searching hard to try to come up with good explanations of such things. And there are many such examples like that.
Yeah, for example, in my talk I mentioned the primordial fluctuations, or the fluctuations in the CMB. So the statistical distributions of those fluctuations are determined by quantum mechanics, quantum effects that mix with gravity, and maybe through observations